I guess I'll just introduce myself quickly and my colleague, and then go straight into it. So we get through this. I'm Jonathan Hunthill, work for SAV Systems, and I'm a sector manager for education, which largely means I look after ventilation for education projects. But more recently, there's a bit more scope of heating systems as well for me. Rob, do you want to?
Yeah, I'm a mechanical design engineer by trade. I'm an account manager for SAV, focusing mainly on heat networks and hybrid plant rooms.
Good.
Yeah. I just want to confirm. Hello, sir, are you recording it?
Yeah.
Yeah, it's on recording.
Okay.
Cool. All right. So I'm going to talk to you about how we can basically achieve Passivhaus standards and BB101 standards for school ventilation. And I want to preface this by saying this sort of assumes that you've got over the hump of using hybrid ventilation in schools, which is not particularly efficient, and are using mechanical ventilation. It just occurred to me, standing in this building, we've got mechanical ventilation here. It is the most efficient way to do things. I don't know why that logic isn't applied universally to schools either. When it comes to Passivhaus, it's not an option. It's not either or. You have to use MVHR. So this presentation sort of assumes that that is where you're coming from. And is my clicker working? Please, yes. And we're working towards this goal of trying to achieve net zero greenhouse gas emissions by 2050, which is a massive challenge. SAV as a company is working very closely with, just going.
Can those online hear us now?
I think so.
Yes, we can hear and see it fine.
All right, thank you.
Okay.
You want to see that here?
No, it's okay.
Did you turn that automatic? I'm sorry.
Yeah, sorry, this is serious technology issues here. I'm just going to reshare the presentation because it's gone. I don't know what's going on with the screen. When
you tap to go forward, are you tapping just once or?
Many times, and I've
Might be a bit of a delay, so maybe just tap it once and then.
So we are working very closely with Scottish schools at the moment. Thank you. Yeah, working very closely with a lot of Scottish schools. So we're currently doing quite a few Passivhaus school projects up in Scotland. There don't seem to be so many in England at the moment, but I think it's a sort of inevitability. And that's largely based on the fact that Edinburgh, being the capital city, of course, of Scotland, has said by 2030, we're going to achieve net zero, probably to one up England. It's normally how it goes. But to achieve that, they've said that all new build schools in Edinburgh must be Passivhaus, and all refurbs have to be to the NFIT standard, which is a Passivhaus retrofit standard. And as you can see, often in England, what happens in London sort of spreads out. In Scotland, we're seeing lots of schools outside Edinburgh also being to Passivhaus standard. And there are a few schools, of course, in England that are doing that as well. That's where we're coming from. We're also thinking about, in the whole scheme of this, the GLA's be seen guidance. Now, that might not be relevant to, say, where we are today, Liverpool, for example, but it has this very logical progression in it. To get our buildings to net zero, we're saying, or the GLA are saying, you need to make those buildings lean, so consume less energy first, then the energy you supply, consume efficiently, and the method of generation of that energy, whether it's heat or electricity, also be done efficiently using renewables. And then you have this sort of offset, which I think I'll gloss over, don't necessarily agree with it. And that's all sort of overseen by the be seen element, which is the ongoing monitoring of buildings. Now, this is what was set out by the GLA, but what we see in countless buildings is skip the first two steps, don't be lean, don't be clean, just continue as you have been and put in the heat pump. If you can shrink your energy consumption in the first place, the scale of your plant is able to reduce. So by following this triangle, we should be able to see much smaller plant installations than we have already. In a passive house context, the idea of passive house is that you essentially isolate the inside of your building from the outside world, which means you have minimal heat loss, and that means that you can minimize your heating plant, for example. So your B lean has shrunk there, and your B green shrinks dramatically as a consequence. So that's the kind of thing we're operating within. Moving on to BB101 and Passivhaus. I suppose it's important to say Passivhaus is not a standard that's specifically aimed at schools. In fact, it's aimed at residential buildings, whereas BB101 is our guidance for specifically for schools for ventilation, thermal comfort, and indoor air quality. So whilst they do align on a few points, you sort of have to see them in their own context. And whilst BB101 is what we need to achieve for schools, we have to make sure we're also achieving the passive house standards. So here are just a few examples of where they are similar. So we have standards for indoor air quality for BB101 and Passivhaus. All air for schools should be filtered before getting into classrooms. Passivhaus says that the casing breakout limit for classroom for any building, is 30 dBA. So that is the same as the SEN standard for schools under BB101, and then both of them have specific limits applied to drafts. So you've got to basically have a comfortable indoor environment, but it is a strange thing here where you've got a residential standard being applied to education buildings. These are the results of a study which I've linked on the screen there, and it showed, this is from the Danish Technical University, so they're one of the leading universities in Denmark, and the field that they're specifically lead in is indoor environmental quality. And what they found is that if you can optimize acoustics, lighting, and indoor air quality together, you can achieve at least a 10% improvement in educational performance. So we're focusing here primarily on indoor air quality, but if you can get the whole environment working together, which is something Passivhaus strives to do, you could easily achieve this 10% increase. And they found for sort of lower performing students, that increase was actually much more, it's something like 20 or 30%. So achieving this trilemma can be really effective. Oh, this is, I thought this slide wasn't here, but that's fine. This is sort of the points we'll cover. I'm not going to dwell on this, bearing in mind we don't have much time, but yeah, I'll cover these in this hour. The first thing I want to talk about is indoor air quality. So what BB101 says is that for mechanical ventilation systems, the daily average CO2 level must be kept under 1,000 parts per million, and you can exceed that for no more than 500 parts per million per day. So when we're looking at sizing, for example, we are looking specifically at what's the daily average CO2 level. And one of our competitors kindly provided a calculator for that with BB101. So it's something you can actually get figures for. Where does that put us in Europe? More or less every single other country has set a hard limit on CO2 that it must not exceed 1,000 parts per million in classrooms. So we're still lagging behind. When we were involved in the reissue of BB101, we made this specific point, but we're still stuck with the daily average for now, which means that the quality of our classrooms ventilation systems is not quite where the rest of Europe is, which is a shame. But I suppose the good news is we can achieve it. Products like Airmaster, which I'll introduce in this presentation, are European products which can achieve these figures and sort of, I hate to use the term, but level up our classrooms. Now, the question is, why does it matter? Why do we care so much about indoor air quality? What's with the 1,500 to 1,000 parts per million? These are results of a study from Harvard University. They did this actually on adults, and the way CO2 works with the brain, the effects of it are worse on smaller bodies. So children would be more adversely affected. But What they did was various tests to determine in this range of CO2 levels, so 500, 900 and 1400 ppm, what or how well people performed in different categories of testing. And you can see very clearly that as the room CO2 level decreases, the performance in each of these categories increases. So if we talk about school environment, applied activity level, focused activity level, information usage, strategy, those are all things that are really going to matter to children in classrooms. And they're all negatively impacted by higher CO2 levels. So this, for me, underscores the need to make sure we're maintaining low CO2 levels in classrooms. So it's just occurred to me, might not be any questions yet, but if you do have questions, please do just butt in. I'm pretty informal. I like to keep the presentations that way. So just butt in if you do have a question. And a question could be, why CO2? Why is it so why does it have such a negative effect on the brain? This is a graph that shows the composition of ambient air. So CO2 level is roughly 400 parts per million. It's important to remember, parts per million, 400 is, 4 times 10 to the minus 10, I think. So absolutely minuscule amount. Oh, no, sorry, that's completely wrong. It's 0.04%, so on the screen, of the carbon dioxide, the air content in the room. So it's absolutely minuscule quantity. And if we look at, okay, what about a room with 1,000 parts per million? We're still talking about 0.1% of the air being made up of CO2. So it's hardly anything. And you could sort of assume, well, more carbon dioxide in the room means you've got less oxygen, and therefore the brain doesn't work as well. But the percentages are, as I said, are tiny. And we've known for a long time exactly why CO2 affects the brain, how it affects the brain. It was discovered in about 1904 by this guy, Dr. Christian Bohr. He was a Danish physiologist, and what he discovered back in 1904 was that as CO2 basically in the bloodstream increases, the ability of the brain to process information decreases. But he worked this out when the ambient CO2 levels were around about 275 ppm, something like that. Where we are now, obviously we've got a much higher ambient CO2 level, and with our net zero goals, we are sealing buildings so that we don't necessarily have a natural exchange of air between inside and outside. So when he did his research, you would have had these buildings, they're leaky, poorly sealed, etc. So you would have naturally had air exchange. And so I suppose back then you could assume that it wasn't a big deal. But now we're saying, okay, net zero, we've got to minimize heat loss. One of the ways to do that is make your building airtight. I've got a specific biology lesson here. So just in a bit more detail, the reason why increasing CO2 levels in the body matter is that hemoglobin is the transport mechanism for oxygen in the body. And basically, as CO2 level in the blood increases, the acidity of the blood increases. And as the acidity of the blood increases, the ability for it to carry oxygen diminishes. So there's an inverse relationship between CO2 level and oxygen getting to the organs of the body. So minimizing CO2, therefore, is incredibly important. And in the classroom, to maintain good indoor air quality, we have to have about 5 air changes per hour. So that's taking the entire volume of air in the room, removing it and replacing it 5 times every hour. And that is a lot of air. For context, you need to change that air. You need to change the air so you have about 725 cubic meters per hour of air exchange. And a cubic meter is actually quite substantial. So you've got a lot of air you've got to take out, and a huge amount you have to bring in as well. And you have to do it with minimal heat loss and also at a comfortable supply air temperature. So you can't just bring in 10-degree air all the time. And that's why natural ventilation is no longer the preferred choice for more or less any building, because all you're doing is expelling heat and then bringing it in at whatever temperature the air is outside. So today, that's pretty miserable. It's probably 11 degrees, something like that. You wouldn't really want to sit with the windows wide open all day. But to achieve 4 or 5 air changes per hour, you would have to do at least that. But the solution exists. The solution is mechanical ventilation with heat recovery. So I'm probably teaching you something you know here, but the principle of mechanical ventilation is that you extract stale air from the room, carry that through a heat exchanger. In that heat exchanger, you transfer the heat out of that air and you expel the air as exhaust air. And at the same time, you bring fresh air from outside at whatever temperature it is. You apply the heat you've just removed from the room to that fresh air, and you put the air into the room at a raised temperature. And that means you've minimized the heat loss from the air transfer from inside to outside. So not only do you get tempered fresh air coming into your room, so a comfortable temperature, but you also have prevented quite a lot of heat loss. And if we look at MVHR, I had a consultant describe it the other day as basically if you have a classroom with MVHR, you can treat that almost a steady state because the losses are so small. Whereas with a natural or a hybrid ventilation system with between 0 and 40% heat recovery efficiency, you've really got to account for the huge chunk of losses that you're going to incur, at least 60%. And as I mentioned before, Passivhaus is very strong on this. They only allow you to use MVHR, and they've done this sort of marketing thing, the case for MVHR by the Passivhaus Trust. But what's interesting here is that MVHR's primary function is ventilation, and in this capacity, it's far more effective at providing good quality indoor air environment, regardless of external conditions and natural ventilation. I think that's really important. And standing here, we've got mechanical ventilation here. It's the only sensible choice. So to that end, we have a Passivhaus component certified product for classrooms. This is the Airmaster AM1000. So Airmaster is a Danish company that's got a range of decentralized mechanical ventilation with heat recovery units. This one is sized specifically for classrooms of about 32 occupants. And as this is Passivhaus certified, it can be used in Passivhaus schools. I'll go into a little bit of detail about the product itself, but mostly I won't specifically talk about it. But we're using this all over the place in Scotland now for Passivhaus classrooms, and of course across the UK for non-Passivhaus as well. In terms of BB101 then, I talked about in my little agenda that I really glossed over the different subjects we'll discuss. And the first one is drafts. So BB101 has applied certain limits to drafts, and what it says is that the maximum allowable delta T between the air already in the room and the air entering the room should be between these limits, 1.5 degrees and 4 degrees, based on your room type. So we have 4 types of room. I'm going to struggle to remember them now. I think category 1 is SEN classrooms, so rooms where people are more likely to be affected by differences in temperature. Category 2 is your standard classrooms. Category 3 is areas of high movement, and category 4 is refurb classrooms. And for each of them, you have a different delta T. So category 1 is 1.5 degrees, 2 degrees, 3 degrees, and 4 degrees. This image on the screen is a sort of typical natural ventilation scenario. So we've said here 16 degrees coming into the room from outside, but in reality, that's just whatever the temperature outside is. It's not a temperature you have control of, and it's also not a flow rate or a velocity that you can control. So what's happened in a lot of buildings is a lot of schools specifically that need a high air change rate is that under the previous BB101, they were designed with a lot of drafts, more or less. So you've got air coming in, say at 16 degrees, and it gets dumped on whoever's sat nearest the window. That's the complaints that the DFE had received. What we do with Airmaster is sort of eliminate that problem. So we make use of the Coanda effect, and this has become more popular in the last few years. Our units typically are mounted right up against the ceiling. And the reason for that is that allows us to use the Coanda effect so we can eliminate distribution ductwork and also use the Coanda effect to have a comfortable velocity and temperature of air. So in this instance, we are bringing in air from outside at more or less any temperature. Because we've extracted the heat from that air, we're able to warm it up before it enters the room. So we've got a temperature coming to the room of 19 degrees of the air. at a high entry velocity, 3 or 4 meters per second. Now, the Crandall effect, what it does, we've got a Wikipedia definition here, is the tendency of a fluid jet to stay attached to a convex surface. And in reality, what that means is if you can flow air across a flat surface at the right speed, at the right temperature, it will stick to that surface for some time. And you could call this a sort of dwell time, how long the air is going to spend up at that point. So while the air is attached to the ceiling, it's able to warm up and slow down as it mixes with the air that's already in the room. That means that, say we have an inlet temperature of 19, as we have on this screen, it will warm up, slow down, and by the time it gets to the occupant, it should be around about 21 degrees, i.e. the room temperature, and about 0.15 meters per second, which specifically meets the criteria of BB101.
Question.
Yeah.
When you bring in the air at that speed, how about the noise?
On our specific units, it's very quiet. So our units measure 35 dBA at 1 meter. There's just not that much
So
noise.
it's whistling across.
No, nothing. They're virtually silent, honestly.
That means if you put a flag there, it's just going to be waving.
It will be, yeah, but there's no noise really associated with it. I tell them, obviously I'm selling something here, but they are the quietest decentralized units on the market. It's important, a sort of context. Airmaster specifically, Danish company, operates in the rest of Europe. We've got the loosest regulations in Europe. They work in all the markets like Sweden, Finland, where they've got, or Germany, where they've got really tight regulations on more or less everything. So noise is very tightly regulated I think it's in Sweden. So they have to have 30 dBA in the classroom. They have to have C-weighted decibel results. So the units are designed to comply with their regulations, the toughest ones. So most of the time you can't hear these units. And for a bit of context, we have one, we operate all the equipment that we sell, but we have an Airmaster, one of several in our conference room at our head office. And sometimes I sit there and I think, oh, that unit's a bit noisy. It's never the unit, it's the laptop fan. It's louder. My laptop is louder than the ventilation unit. So they are really quiet.
That means your laptop is lucky that you had it.
Yeah. Airmaster didn't make the laptop. The Crandall effect is very useful. And we can see in this image, it's a very Danish classroom, but this is a typical installation. You can recess them, and I'll come back to that. But in this instance, having no distribution ductwork means we have basically a simpler installation, but also you need lower specific fan power because you don't need to push air through ducts in the classroom to be able to distribute it. So compared to other mechanical systems that use distribution ductwork, the specific fan power should be lower.
They're quite visible there.
They can be, yeah. They're not always. I've got some images at the end of the presentation to show you how we integrate them. But I would argue that visible ventilation isn't necessarily a bad thing because it makes people aware of it, aware that it's important. Okay, so next slide, I'm just trying to get my bearings. Next slide is about nighttime cooling. So the overheating criteria changed quite a lot from the previous BB101 to the current one. Previously, it was basically the sizing from TM52. They moved away from that, and they now say that delta T should never exceed 1 degree Kelvin for more than 40 hours per year in that specific period. Previously, I think it was 200 hours for the entire year. And then you had the two other criteria from TM52, which, to be honest, were being phased out when I started working with Airmaster, but they were a maximum limiting temperature. And I think there was, this one is hours of exceedance, and there was one other that I can't remember the name of. This comes up a lot, the overheating question, and what the DFE says is that the building should be designed as much as possible to passively prevent overheating, i.e. you're not relying on your ventilation to do that. I think the key thing here is not necessarily the ventilation, it's actually about solar shading. It's about thermal mass of your building, maximizing the thermal mass. And if we look specifically in the context of passive house, it's also about orienting the building so that you minimize thermal gains from the sun. So in that sense, the ventilation isn't that important. However, as more or less any ventilation system would do, an air master will do nighttime cooling. So it will try and cool down the thermal mass of the building overnight. And I had someone say to me once, well, that doesn't really work because you still get to your peak temperature. That's true. You still get to your peak temperature. But if you think that you have a big concrete slab, which has been cooled to say 14 degrees overnight, during the subsequent day, that slab will warm up. Instead of warming up the air in the room, you warm up the slab. So it's acting as a heat sink, drawing in heat. I had this Australian guy say to me, well, in Australia, we build our buildings really lightweight so they don't overheat. So yeah, you're not an engineer. You are really wrong, but I'm not going to tell you exactly why. I don't see the point. But for millennia, people in hot countries have been building their homes with huge, thick walls because they absorb heat. So they are cool in the day and warmer overnight where they expel heat. We can apply that principle in the UK, even though it's not very warm. And we probably didn't need to know that, bearing in mind the climate conditions we've had here for millennia. But that is the best way to prevent overheating. Instead of relying on your ventilation to do it. The reliance on ventilation is a consequence of lightweight buildings specifically. I'll stop. Got on a bit of a thing there. But in terms of indoor air quality, then BB101 says that F7 filtration is the minimum recommended standard for schools in polluted areas. I want to highlight a couple of things here. Firstly, F7 is no longer a standard. This M, F, and I think that was G. Those standards don't apply anymore. That was EN 779. We have a new standard now. It's called ISO 16890. And this was released just before BB101 was re-released in 2018, but they chose not to update it. So what it says is that essentially every filter should be graded on how it performs. Anecdotally, I was told by a guy from Camfil, who are a big filter manufacturer, that an M5 filter could easily be anywhere between 20 and 80% efficient, which is a huge range. It means that the quality control just didn't exist, more or less. What ISO 16890 aims to do is really clamp down on that. So this EPM 10-50%, for example, means that the filter must filter out a minimum of 50% of 10 micron particulates. So it's really specific on what you can do. So yeah, on the F7 equivalent, you have to filter out at least 55% of 1 micron particulates, which are obviously even smaller than 10 microns. For passive house, then, it says all air must be filtered, but the minimum standard for passive house is F7 or EPM 1, 55%. Whereas in schools, you can actually get away with no filtration, but typically people do EPM 10, 50%, unless it's a known polluted environment. So maybe central London. I just want to make a comment here about air quality. It's said to be responsible for about 4.2 million deaths per year. It's a crazy number. And we had in the last few years the first legally certified people who died of poor air quality. One thing to highlight is that I suppose the frustration I have, it seems that people are thinking, well, electric vehicles will solve this problem. Yeah, it's not true. DEFRA has found that they, if not equal, supply more localized pollution into the air than petrol vehicles or sort of petrol diesel vehicles do. And that all comes from tires and brake dust. So I wouldn't be...
Electrons as well.
I suppose they're electrons, yeah. And then, of course, you've got decentralized generation of the electricity and the pollution that creates. So don't be fooled into just thinking, well, with electric cars, we don't need to worry so much about pollution. It's simply untrue.
No, but typically what they're looking at in pollution is looking at the particulates from the carbon, diesel,
Right.
So it's not necessarily the tires or the brakes and all that. It's the particulates from those. And when you look at
Combustion.
in terms of brakes and all that, you have speed control. That will limit how much braking you're able to do.
Okay.
So it's not necessarily, so the electric will still solve that problem. So I know where you're going to in this case, but the electric will still solve the problem.
Okay.
Because the particularly from the diesel is not there anymore. And also from the carbon stuff. So
I suppose the point I was trying to make was we're still going to need filtration. The need for it's not going to go away.
yes,
It may diminish, but it's not. You can't assume that air shouldn't be filtered.
if you're in Wales, you won't drive 20 miles, so you won't can even brake using your
No. Right, if you're in London, you get into the 20 zone and slamming your brakes on, and
Oh, it's frustrating in London.
Yeah.
You hit every street light, I mean, every traffic light, just take. I'm sure you know about
are you from London?
No, I'm from Essex, but
Okay.
that.
I'm from Surrey, so yeah. So that. So just in terms of Airmaster, this is you can see this is a semi-recessed installation. This is quite an old installation. And I say that because we've got 2 units. Typically, we can just do it with 1 unit nowadays. And again, it's a Danish classroom in this instance. But we tried to make filter change as easy as possible. So that on the bottom surface of the unit, that's a service hatch. And to change the filters there, you just open the hatch, pull the filters out, put new ones in, and put the hatch back up. So it's made as simple as possible. And on the control panel as well, you get a notification to say that filter change is due. Then you have about 3 months roughly to change the filter. If it's not changed, then the unit will turn off to protect itself. So you have this long warning coming up to it. I suppose it's worth saying with mechanical ventilation units, they don't necessarily filter air for indoor air quality. It's normally to protect the components of the air handling unit to prolong the life of it. But it then has a dual benefit for us of being able to filter incoming air of pollutants so that the air that comes into the classroom is always clean. In terms of noise then, these are the standards. So 35 dBA in BB101 for standard classrooms and 30 dBA for SEN classrooms. But for Passivhaus, as I mentioned earlier, 30 dBA is the flat limit. So when we talk about our ventilation units, specifically in Passivhaus schools, we have to supply them limited already to 30 dBA. They're not allowed to go any louder. So in terms of the sizing here, we end up going up a unit size because we have to reduce the capacity to achieve the noise levels that the Passivhaus states. But I would like to point out, I've highlighted it here, these numbers are measured at 1 meter from the unit, and all our competitors will measure at 3 meters from the unit because you lose about 3 decibels over those 2 meters. So they are always quieter than the competitors' equipment. And we don't expect to use any attenuation whatsoever because the unit itself can attenuate 49 decibels of noise. And that's made possible because firstly, they're very well acoustically insulated, but secondly, having a heat exchanger there, you take out loads of the kinetic energy of the air coming through the unit, which has got a lot of noise in it. So just by virtue of having a heat exchanger, you can cut out loads of noise. And in the early days of Airmaster in England, loads of our projects were, we've got a noisy, we've got an A road next to a school, it's too noisy. One side of the building has opening windows and the other side needs to have huge attenuation on it. So there's big disparity between indoor air quality between classrooms as a result. I want to talk about here energy specifically. So according to this building energy efficiency survey from about 2015, this is how energy has been consumed in schools. So 55% was heating. And I think it's reasonable to assume that is primarily caused by having natural ventilation in schools, which would have been allowed at that point in time for those schools. If you can apply heat recovery ventilation to that with an efficiency of 80–90%, oh, here, sorry, I've done 75%, you could achieve a 41% reduction in how much heat is consumed. So if we think back to the earlier slides, this is the B lean, reducing heat loss, so reducing energy consumption. So in terms of our B lean step, heat recovery ventilation is incredibly important. I've put 41% reduction here. That is 41% in overall energy consumption for that building. So that'd be taking 100 kilowatt hour per meter squared building down to 69, for example, sorry, 59, for example. So it can be incredibly effective in reducing schools' energy consumption. And the benefit of that is that your heating plant diminishes enormously. So this is on the right hand side, I took a snippet of a report from a consultancy. It's not anything that we generated, it was from them, and we were specified for it. They compared mixer boxes, a school with mixer boxes to a school with Airmaster, and they achieved on that project a 64% reduction in energy demand due to ventilation. And it's important to say that energy demand due to ventilation is composed of heat and fan energy. So it's both things. My competitors will probably tell you it's fan energy only because they have very low specific fan powers. But you have to remember the ventilation causes heat loss, and therefore you have to look at it holistically. In this case, theoretically, they were able to take out 455 PV panels, which would have generated all that heat. And it also would have cut down, they didn't quantify in their report, but it would cut down an enormous amount on the number of heat pumps they had for that project, which is great. So in terms of passive house specific ventilation, you really have two choices. You've got centralized MVHR or decentralized MVHR. This example here, all these kids on the screen, this sort of serves to demonstrate how different the classroom is from, say, a residential application. You've got 32 people in the room. They go in, they come out, demand changes all the time, very rapidly. And that means that firstly, your heating has to be up to the task of being on and off very quickly, but also ventilation has to do the same. And demand controlled ventilation here can save a lot of energy. So demand controlled ventilation just means linking fan speed to an element of demand, which in classrooms is nearly always going to be room CO2 level. This is the profile from a school that we took out of a data logger. And the green line is your supply airflow rate, and the yellow bars are your room CO2 level. So firstly, you can see here that CO2 level didn't exceed 1,000 parts per million, so that's good. But also, the fan speed varied throughout that day. My experience, centralized systems are rarely set up to modulate. They're nearly always at a fixed flow rate. So everything that's I'm now highlighting grey would be energy that was consumed by a centralized system that wouldn't be consumed by a decentralized system. And I suppose to explain the reason for that, it's challenging to the extent that people don't bother doing it to have changes in a centralized system, more or less because if you say, okay, these rooms are all set up for maximum capacity, and then one of them empties out, and you don't need air to that room anymore, the pressure is then, you shut that classroom off. The pressure from that classroom is going to be distributed to all the other classrooms, and then you have to have dampers that adjust accordingly to prevent you supplying too much air to the other classrooms. And what inevitably happens is people say, that's really complicated, we'll just go for fixed airflow speed to all the classrooms. And I say this from experience because we lost a passive house project in Scotland to a fixed airflow rate centralized system, and I was horrified and yeah, not particularly happy. So it happens more than we'd like.
Yeah, I'm just thinking it's not all the application that will suit decentralized system.
Mm-hmm.
But you have some application that you really have to, because with your system now you're looking at the headroom, which there must be a height for the room to be. So if you have a room that is not that to that specific height, and you haven't got the ceiling space to put it in, then you might find that that may not necessarily be the right solution for that application. So you'll have that as well. So more so, like you were saying, that if one of the demand in a room is lower, that you think that the air gets redistributed to other rooms. But it seems not balanced then. Otherwise, the main issue that is providing the motive force will modulate as well to respond to the lower demand rather than redistributing it. You know, if you have a fixed system, which is a cheap system that you're saying, if it's they're looking at their budget and they don't want to really balance, they just want every room to have the same volume going through. That is not going to work.
That happens all the time.
Yeah, I know, but people make wrong choices and they later now blame the design on, but rather they value engineered it to suit the budget size.
I think the point about headroom is not something we come up against that often, because when we have a suspended ceiling, we recess the unit partially into the ceiling. But there's also areas in a classroom where no one's going to stand there. But, you know, if you put a cupboard underneath, for example, okay, that would be a problem for us. But you can find areas in the classroom where headroom is not necessarily an issue.
It has to be close to the window.
It does. That's true. We've got lots of classrooms though. Air masters in them. Just in terms of the energy savings then, so I've compared here an air master and a centralized system at a constant volume. Their specific fan power is generally about 2 watts per litre per second. We're typically about 0.9. So immediately there's a huge saving there on specific fan power to be had. So dropping from 3.2 to about 1.4 kilowatt hours. Sorry, I should say kilowatts. I keep meaning to change it. It's kilowatts. If you apply the demand control profile to that, the savings are much more substantial. So here I had to take an average flow rate for that day, 151 litres per second, but that gives us a specific fan, 0.6 watts per litre per second. So for the same classroom with effectively the same indoor air quality at point of use, we've saved about 78% electricity demand between those two systems. So there's dramatic savings to be made. If you can go, firstly, if you can go variable volume, but secondly, if you can also go decentralized and take advantage of low specific fan powers.
Just to make it clear, is it the centralized and decentralized? Is that depending on the position of the unit in the room?
So centralized system is what we're having here, for example. So we've got an air handling unit on the roof, and you've got ductwork running through the whole building to deliver air to each room. The decentralized system is putting the unit in the room you want to deliver air to.
Okay.
So when you think about how you transport the air, that's what really the difference is. So for a centralized system, you have all this ductwork everywhere. It's massive. You have to run it through your whole building. That's a big, in terms of work involved, that has to be coordinated, that has to be installed. So it's quite a substantial undertaking. The decentralized system, most of our projects are refurbishments, because you can say, okay, I've got this classroom. We have no scope to put a centralized unit and run ductwork everywhere. We just put it in this room, where's the external wall, and we just supply air straight through. So we end up with a duct run that is probably 300 millimeters through the wall, instead of taking air from the roof all the way through the building, all the way down to your classroom. So for the amount of pressure you need to deliver those two things is completely different, and therefore your specific fan power can be vastly different. Just want to mention a couple of things in terms of design considerations, because Passivhaus is so specific in so many ways. This is one of the considerations we have to think about a lot, which is having penetrations through the building. So Passivhaus wants you to minimize how many penetrations go through the building, which makes good sense because you want to prevent heat from going from inside to outside. And with Airmaster, we have a pair of ductwork connections on every classroom or every unit. But you can prevent that. So in this case, we've sort of volunteered this universal pipe collar. You can use this to wrap around the duct as it penetrates the wall. And in this case, they have an air leakage through the duct of 0.25 cubic meters per hour. which is 0.3% of what you're allowed in total. Now, to add to this, I haven't updated the presentation yet, but recently an Airmaster unit was put in testing by 5 tier 1 contractors in Scotland working on passive house schools to see what the air leakage of the unit specifically was. And they got 0.06 cubic meters per hour, so incredibly low, and therefore very much compliant with the standards. And in that instance, they're trying not to use centralized systems. There's also a risk of thermal bridging, so having metal that's carrying heat from inside to outside, for example, that's not allowed on passive house again, and they spend many hours getting rid of the details that enable you to have thermal bridging. So we recommend having a rigid plastic duct instead of metal, which we'd use on a typical building. Essentially, that means basically a very large soil pipe, because that's the easiest way to get a very large diameter pipe or duct. I'm focusing here now specifically on Airmaster as well, as we sort of come to the end of the presentation. We put some brochures on the table. We have an online monitoring platform for Airmaster, which basically allows us to monitor the units to see how they're performing, if they have, from an operational sense, if they need filters change, if they're in fault for any reason. I won't go into this really, but it's very useful for us to be able to monitor what's going on without having to be in the specific building. And it can save huge amounts of time.
Another question. In terms of the inlet and exhaust air, how does this unit reduce cross-contamination?
So the calculated cross-contamination between intake and exhaust is a maximum of 4%. In practice, it's been measured at less than that, but the way it does it is we have the two external connections. They're about 1.8 meters apart. On the intake, the fan is located quite far into the unit, so the pressure at the spigot is actually quite low. Whereas on the exhaust, the fan is located right at the spigot. So at the exhaust, it shoots out the air as a jet at very high velocity and a high pressure. So because of the vast differences in pressure and also this jet, we find they don't really recirculate at all.
So it's not based on what is happening outside. So if there's a headwind or gale forces and all that.
That actually helps. That helps because the air that's being jetted out is carried away immediately. I can show you after the presentation. I've got a slide on it, which is not in the presentation. I can show you to explain it better.
Because 1.8 meters apart, that means your unit must be really massive then.
Quite big.
Achieve that. That means at least it'll be about
2 meters wide.
2 meters wide.
The passive house one thing. Yeah, the ones not for passive house are smaller than that.
What was the kind of weight?
Top of my head, I can't remember.
1 ton.
No. We're talking about a couple of 100 kilos. But it's important to remember we are typically only using 1 unit per classroom. We're not.
I understand. I'm only thinking of in terms of installation on site and the kind of fixtures and the kind of structure that you suspend it.
So what we normally see is people fixing unistrut to the ceiling or to beams, whatever's available. They'll fix unistrut on and they'll fix our unit into the unistrut and suspend it from that.
So if you're looking at hundreds of kilograms, that means you need.
We're talking about maybe 200.
That's heavy.
It's heavy.
Don't want to drop it.
No.
Yeah.
Installation on site is generally pretty smooth though, because once you've made the holes and you've put the mounting hardware up, you can just make that stuff together, put it up there on a lift, I suppose.
Oh.
I
thought you said two-man lift.
Yeah, just lift it above your head. It's normally pretty quick. So one of the big benefits of Airmaster is a quick installation, and there's no real commissioning process because if we just have a connection through a wall, 300 millimeters, say, there's no pressure drop to speak of except for what the grill has. So the fans, the throughput that we claim on our data sheets is very easily achievable. The data sheet condition is almost always the same as the installation condition.
in terms of the coils inside. So
We have a heat exchanger. We don't typically put any other heating coils in there. We can't do space heating.
so it's electric heating.
No, we don't do space heating through our units.
Right.
We only try to, we have a new unit that can do that, but it's not one that I want to talk about because it's basically not suitable for schools. But we're not trying to do space heating through our unit. We're expecting the room to have radiators as well for heating already. And we're purely trying to provide the ventilation as efficiently as possible.
Cooling as well.
So we do have cooling modules available, and they're very smart in the sense that they are fully integrated, a single box that is in the room. There's no split, but the GWP is enormous to the point where I don't want to sell them because I think it's irresponsible. So yes, we can do cooling, but I don't think we should.
Okay.
I've just got a few case studies here to show you. I'm conscious just run over the hour. This is First Down School. It's a special needs school in Winslow, which is Buckinghamshire, I think. And here, this is another fully exposed unit. And the reason why they used Airmaster here is twofold. Number one, they've got lots of thermal mass available, but this is actually a really well-designed project for lots of reasons, unrelated to Airmaster. But they've got lots of thermal mass. They've got their exposed ceiling surface, which means that, again, you've got thermal mass there. But the reason really why they used Airmaster was because it's so low noise. So these will be limited to 30 dBA. And as I said, I've been to this school several times and it's a very nice environment. This is a school that's in Maidstone. So you might not be able to see it, but there's an Airmaster on the top left there. They've somehow managed to get the ceiling looking like an Airmaster. I don't know if that was intentional or not, but they had two criteria here. This is like a Georgian building, I think, and it was overheating massively. So they put in Airmaster and stripped the building back so the thermal mass was exposed. And anecdotally from that consultant, they say they've seen a huge improvement in overheating, i.e. they've massively reduced overheating in those classrooms, which is great. The thing we didn't know at the time was Maidstone itself is the most polluted place in the UK. When you think about it, it's next to Dover. So all the lorries queue up to get on the ferries to go across to France and the rest of Europe. So they have huge amounts of pollution. So in this school, they've now got filtered fresh air entering their rooms. So the children aren't sat in a really polluted environment all day, which is very nice. We're pleased for that. Yeah, we're pleased when we found that out. And this is a semi-recessed unit. The reality is most of our projects, we have a recessed unit or semi-recessed unit. So here they had limited ceiling height. They did have a suspended ceiling, so they're able to semi-recess that unit. Now, I should say here, we can fully recess the units. Of course, then you have to have a supply duct and an extract duct in the room within the suspended ceiling, but it is possible to have them completely recessed. And another option would be if you could have a ducted extract, but you could have a perforated ceiling grid and use the ceiling as a plenum chamber. So you just flow air straight into the ceiling, into the plenum, and let it come out through the ceiling surface, and then extract through the specific extract grill, which can be a really nice installation there with a concealed unit.
You have to duct the air. I know you were saying
Yeah,
in terms
small
of
pressure
your the velocities
Mhm.
different between inlet and outlet. How do you now adjust the fan speeds to, if you have to duct it, say 2-3 meters?
We wouldn't adjust the fan speed. I mean, 2 or 3 meters is not going to create much of a pressure drop, probably a couple of pascals. So
Yeah, I'm looking at the cross contamination outside.
oh, outside. So in that case, we would still probably expect the unit to be on the external wall.
So that means you have the flexibility.
Units doesn't
The
matter.
flexibility of actually moving those ducts to give you the biggest pressure distance.
To be honest, we haven't had to deal with that at any point. We've got lots of installations where there's a bit of a duct run, but we try when we're working with the consultants to say, okay, can you minimize that? Because generally there will be a reason why they've done it. but I find a lot of people saying that putting the unit in the middle of the room for some reason. What you want to do is put it on the sort of as far from the centre of the room as possible, the longest throw. If you're thinking specifically in terms of cross contamination, and what if you ducted your grills inside the room? There's no reason there why you couldn't have the unit right up against the external wall and only duct it after the supply grill into the room.
No, I'm not looking at
No, I know.
I'm looking at the intake and,
Yeah.
and the exhaust. That's what I'm looking at.
But we would try and design away the problem. Otherwise, we wouldn't change the fan speeds. But we would try and keep it on the external wall as much as possible. Keep the duct runs to a minimum. Got very quickly sort of installation video. I don't think it comes across very well on Teams. But this is, unfortunately, these pens don't exist. But this is the level of simplicity we aim for. And that is, yeah, really how we'd expect most installations to be.
When it's semi-recessed, do you turn it the other way, or is it different unit?
So,
In the recessed unit,
yeah. Oh, yeah.
that configuration is different, or do you just invert it?
No, so actually there's plates on the inside that direct the airflow either to the top, the centre, or the bottom third of the unit. So we change the position of the supply grill on the front, and then inside we change where these plates are, which direct the airflow. So no, we don't flip it upside down. We move it, and
All right.
it's part of the internal configuration.
All right.
So I'm wrapping up here. Hopefully all of that helps us get to our 2050 net zero goals. I think, yeah, based on all the work that I do, I think really what would help enormously is if we stop consuming so much energy and then we started applying pumps, for example, to a reduced scale of energy consumption. That Danfoss estimate that we're wasting about 30% of our energy, just on waste by consuming heat when we don't need it, for example, overheating buildings, that sort of thing. So there's a huge amount that can be done just to cut energy consumption in the first place before you start to look at how you generate that energy. And I would advocate as much as possible to prevent energy consumption before looking at the energy generation. We have some literature. We produced this document a while ago to explain this is aimed at schools specifically, to say to head teachers, parents, etc., why having good indoor air quality is so important, because we don't think it's understood as well as it could be. And then we specifically have documentation about decentralized ventilation and why we think it's the best solution for lots of projects, not all of them. We also at the time made some school lessons which are available online, and bizarrely they've been very popular. We're a bit surprised when we went and looked, but they're specifically about air quality and also about how we use resources. But I just mentioned this because we're trying as much as possible to be involved in education for schools, for anyone. And that is it. So thank you. If you've got any questions, anyone remote got any questions, please do just ask. Otherwise, yeah, thanks for your time.